Gustavo Burdman. Sorry, no, Gustavo is not an organizer. He's a lecturer. Enrico Nardi is another organizer. He'll be here later today because he just arrived from Italy, so he's jet lagged. And Géraldine Servan is the other organizer, but she will not be here. Maybe she'll be online. You'll see about that. So, so I have a few announcements here. So this is the building of the Institute of Theoretical Physics from the University of São Paulo, from the State University of São Paulo. And we are part of the South American Institute for Fundamental Research, which is affiliated to ICTP in Trieste. And this is an activity organized by this institute, the ICTP-SAIFR, as you probably know. Yeah, so I want to thank you, Gustav Burdman. He's here. We had a change in the program because of situations that were unforeseen, and Gustavo Burdman accepted to give lectures at the last minute. So I want to thank Gustavo for this. Okay, so maybe some announcements. Right. So if you want to get a key, there's some lockers that you can use to put your backpacks, etc. I think you have to pay a deposit, but then you can see the secretaries there. Yeah, so we are broadcasting on Zoom, etc. And what else? We are going to have a social dinner, and that's on Thursday. So at some point I will circulate a sheet of paper for the people that are interested to sign up. It's free. And this includes one non-alcoholic drink as well. It's churrascaria. So all the attendees and lecturers, of course, are invited to come. This will be on Thursday. So we also have discussion sessions at the end of the day with the lecturers, so that you can ask more questions about the content of the lectures. We also have poster sessions. We have sessions where students will give talks. And also today we have this ice-breaking session. The idea of the ice-breaking session is to introduce ourselves. Because I think one of the important things we realize in this type of event in schools is to make connections that may last for your whole life. You know, it happened to me, it probably happened to Gustavo and Sheng, that we met people in schools when we were students, grad students, and we kept friendships for the whole life. So this is something that I hope will also come out from this. And also, you probably noticed it's a holiday here in São Paulo, so things are pretty much closed everywhere. Also, one thing I want to tell you to be understanding is that we don't have the cleaning crew today because of the holiday. So please be understanding that today there's no cleaning, but the other days it will be normal. So so you have some information on your bag about restaurants, etc. They're mostly closed today. There's one that's always open. It's the barbecue place, something grill. I forgot the name, but you'll find. I can tell you later where to find it. Okay, so very good. I'll be the chair of the first lecture of today. So let me introduce you. We have very honor and pleasure to have Professor Mikhail Shaposhnikov. So let me say a few words about Misha. So he goes by Misha. I think it's okay, no? So Misha, he did his PhD at Moscow State University, an Institute for Nuclear Research of Russian Academy of Sciences. And he worked in several places at CERN, and in 1998 he was appointed professor of theoretical physics at the University of Lausanne, and since 2003 he's a professor at Lausanne, leading the Laboratory for Particle Physics and Cosmology, and I think now he's emeritus. And Misha has done fundamental work in this field of electroweak baryogenesis. And but here he's going to talk the basics of cosmology and things like that. So he also got several prizes. He was a recipient of the Andrei Sakharov Gold Medal, awarded by the Russian Academy of Sciences. He also he was awarded the Markov Prize for Fundamental Physics, and also the Humboldt Research Prize awarded by the Heidelberg University. So it's really a pleasure to have Misha, who is going to give you some basics about cosmology. So please, Misha.
Thank you very much, Rogerio, and thank to all organizers to giving us an opportunity to be here in São Paulo. Good morning, everyone. So I was asked, and I will deliver here lectures on the basics on cosmology. And so I will tell you not only about the stuff which is relevant for our existence, for baryon asymmetry of the universe, but also about other things, okay? About standard, more or less standard cornerstones of cosmology and some of its cosmology development. So why so? Because I believe that everything should be considered as a package, okay? So if we want to understand baryon asymmetry of the universe, we presumably would like to understand other things as well, such as dark matter, perhaps dark energy, structure of the universe as a whole, etc., etc. Okay, so first of all, now cosmology is very tightly related to particle physics. At first sight, this relationship seems to be rather bizarre, because you say, okay, particle physics is dealing with the distances which are very, very small and studied experimentally at, say, different particle accelerators, whereas cosmology is something which is associated with very large distances of the order of scales of different galaxies, cluster of galaxies, etc., etc. And there is a huge mismatch between the energy scales which appear in these two different directions of physics. So why they are related? They are related because we know that the universe right now is expanding. At present, the universe is not very dense. Okay, we have roughly 1 proton per cubic meter, but if you look in the past, you found out that everything gets together very close, and therefore the universe was much denser in the past, and since it was much denser in the past, elementary particles were close to each other. They interacted between each other, and here where the particle physics comes into play. So in a sense, particle physics determines the structure of the universe, how we observe it today. And not only that, we have another direction. By looking at the universe, how we see it today, looking at their different characteristics, we can try to guess and we can try to get some information about particle interactions at very high energies. The famous Soviet cosmologist, Yakov Zeldovich, he used to say that universe is a poor man accelerator. So it can produce very heavy particles, the particles which we cannot produce, and we will never able to produce in particle physics accelerators. It can also produce very weakly interacting particle, interacting very weakly than neutrinos. So the trouble here is that we cannot repeat this experiment because the Big Bang, the universe exists just in one unique piece. Okay, so here is the plan of my lectures. I don't know if I will be able to carry all of these points, but we will see. So I will start from necessary elements of general relativity. Well, I should stress, but that my lectures will not be technical. Okay, I'm not going to really derive and demonstrate to you the flow, how the equations are appearing. I leave it to you, or you can ask me a question and I can go on the blackboard and tell you what different details are. So my game is to tell you about some qualitative features which are important and perhaps teach you how to do order of magnitude estimates. Okay, so this is my basic goal. So what I'm gonna do first, I will remind you necessary elements of general relativity. Then we will discuss structure of the universe at large distances, Friedmann equations, and we will discuss the content of the universe from what the universe is constructed from. And then we will come to the part which is very relevant for the topic of the school, origin of matter, foundation of Big Bang theory. Perhaps the most important part here will be freeze in and freeze out of particle reactions. And we will see that with the use of relatively simple estimates and common sense, you can understand many things in cosmology, such as cosmic microwave background, the neutrinos. We will estimate the number of neutrinos in the universe today, Big Bang nucleosynthesis, okay, baryogenesis. There will be a lot of lectures on that, but I will say still a few introductory words on this subject. So dark matter, dark energy, inflation, perhaps vacuum instability. Okay, so this is my plan, and we will see how it goes. So, Richard, a question. The questions are coming in the flow, or it should be went to the end of the lectures? Yeah. So please interrupt me at any stage. Ask questions if. Just raise. Okay, so cosmology is based on general relativity, okay? How do we get general relativity? If we take distances in three-dimensional Euclidean space, okay, that's what we learned at school, then in Cartesian coordinate, the distances are simply given by the dx squared, dy squared, dz squared, okay? So generalization of that to four-dimensional Minkowski space-time is the following. You go from the distances to the interval, and interval is the quantity which doesn't change if you go from one reference frame from one inertial reference frame to another. And it's given as d time square minus d distance square. Okay, yeah, I should stress that everywhere I will be using natural units in which h bar equal to Planck constant equal to the speed of light equal to 1, meaning that everything will be measured in GeV being the unit of energy. Okay, so once you see this formula, you want to write it in some compact way by introducing the Minkowski metric. Okay, so and here you see mu nu, and repeated indices are summed up. This is the Einstein convention to simplify complicated formulas. Okay, so now if you go out from four-dimensional Minkowski space-time, and if you want to use arbitrary coordinate system, not necessarily Cartesian, it can be spherical coordinate system or just arbitrary coordinate system, then we can write the interval, and this is the quantity, invariant quantity, which doesn't change if you go from one frame to another, as in this form, and G mu nu is the metric. This is an arbitrary function of space-time coordinates. Okay, and these space-time coordinates are not Cartesian anymore. So, and now this is exactly how general relativity is constructed. Instead of saying what the metric is, you say that this is now a dynamical quantity which is determined by some dynamics. Okay, we will find out what this dynamics is. So this quantity is not God-given, but it depends on the distribution of matter, and it depends on the distribution of gravitational field, which is in this case the metric G mu nu. Okay, how this dynamical theory is constructed? It's constructed in the following way. You say that the interaction of the metric with everything else should be such that the theory is invariant under general coordinate transformations. Okay, so whatever coordinate system you choose, you go from one type of coordinates to another type of coordinates, and you make this dependence arbitrary, and then you require that your dynamical theory remains invariant if this transformation is weight. Okay? And this is a very, very strong statement. I mean, once you accept that this is the case, you get that the equivalence principle is mathematically satisfied. So equivalence principle is equivalence between, say, inertial mass of the bodies and gravitational mass of the bodies, or equivalence between acceleration and gravitational fields. Okay, so once you have equivalence principle, this means that you can remove, say, action of gravity by the choice of a particular coordinate system. I mean, like the lift which is falling down, you can always go in this frame, and then in this frame you will get no action of gravity. So actually, there is a very profound analogy of this construction with the standard model and with electrodynamics. So the standard model and electrodynamics are both gauge invariant theory, meaning that the dynamical variables in this theory can be changed in some local way. So for electrodynamics, this is just a gauge transformation. You add to A mu, D mu alpha, and then the whole theory is gauge invariant. And this is very, very close to what we have in gravity. Okay, so once you said that, you can, after some manipulations, construct the theory of everything. Okay, theory of everything, well, okay, quote unquote, would be a combination of two types of action. So one type is a gravity action, and another type is the matter action. Okay. So what the gravity action is, since we said that everything should be invariant with respect to coordinate transformation, you can search for the quantities which have this property, and the quantity which has this property is a constant, which is associated with the cosmological constant. Okay? And yet another piece is scalar curvature, and R is some combination of the metric and its derivatives. Okay, and this combination is organized in such a way that this guy doesn't change when you make the coordinate transformation. Okay, and then the matter action is certainly action of the standard model, plus some other stuff which we have not discovered yet. Okay, and then the sum of these two is potentially describing all phenomena which we have in the universe. Okay, so this formula just shows how the scalar action is constructed from so-called Riemann tensor, okay? And Riemann tensor has a very, very close analogy with Maxwell tensor in electrodynamics. So Maxwell tensor in electrodynamics can be constructed as a commutator of covariant derivatives, and also the Riemann tensor can be constructed as a commutator of covariant derivatives, but now in gravity. Okay, so once you have this action, theory of everything, you can proceed and derive equations of motion of your system. So how do you do that? You take the action and you find the variation of the action with respect to different dynamical quantities which appear there. So metric in particular, okay? And that's what you get. You get, you find the variation of the metric, and you find the Einstein equation, which is contain R mu. R mu is a Ricci tensor. So here I contracted all indices to get scalar curvature, but if you contract just two of the indices, then you get the Ricci tensor. Then there is yet this part, there is this part, and there is right-hand side of these equations, which are very important, and which actually gives you the relationship between matter and gravity. And this part here is nothing but the variation of the matter Lagrangian with respect to the metric. And so this quantity is called stress energy tensor or energy momentum tensor. Okay. And so if you do the same in electrodynamics, left-hand side will be derivative of the Maxwell tensor, and right-hand side will be the current. Okay, so we say that the current sources electromagnetic field. So here, stress energy tensor sources the gravitational field. And yeah, once you have it, the space gets curved. And how the space gets curved, you can find from the Einstein equation. Okay, so that's how Einstein theory is constructed. It gives us a relationship between matter and gravitational field. And now we can be very ambitious and apply this Einstein theory for description of the universe. Okay. How do we apply this equation to description of the universe as a whole? So to understand that, we should first try to see what kind of scales, distance scales, we have in the universe, how they are related to each other. Okay, so if we look at the universe just nearby us, we will find that the universe is extremely clumpy, right? There is Earth, a lot of stuff in the Earth. There is nothing, then there is sun, then there is galaxies, etc., etc. So the universe is very, very clumpy and non-homogeneous at the scales of the order of Earth radius, of the order of solar radius, of the order of Earth orbit, because these are all the structures associated with solar system. It's also very clumpy at the scale of the size of galaxy, which is a few kiloparsec or so. So parsec is 3 something light years. The universe is clumpy at the scale of cluster of galaxies, at the structure of the size, which collects different galaxies connected to each other by gravitational interaction. But if you look at the very, very large distances, much larger than the distances of the cluster size, much larger than 5 megaparsec or so, we will see just from observations that the universe is homogeneous and isotropic. Okay. So how can we check that? Isotropy is something which is relatively easy to check. Okay, you look at the different distances from the Earth, and you find how many galaxies and what are their distribution on your light of sight. Okay, so that you can do. This is some nice pictures which shows the sky, and here is different directions, and it looks pretty much isotropic. So you have to exclude this part, which is our galaxy plane. Okay, now, if you the same result you get from the study of cosmic microwave background, which we will discuss somewhat later. There is a relic radiation coming from all ports of the sky, which has the same temperature in all different directions with accuracy of the order of 10 to the minus 5, which also shows that the universe is isotropic. You can also check the homogeneity of the universe. Homogeneity is somewhat more complicated because in order to check homogeneity, you have to know the distances from you to a particular object in the universe. And distances, it's more difficult to measure than simply the angular distribution. But this also can be done. And then what you conclude is that the universe is homogeneous and isotropic if we consider the distances which are larger than the size of the cluster of galaxies. Okay, so why I'm discussing all that? Because this gives enormous simplification if we want to study the universe at large distances. Okay. So one thing, if you have something clumpy, imagine in electrodynamics, you want to find electromagnetic field coming from some complicated distribution of electric charges, so that can be challenging. But now if you say that everything is homogeneous and isotropic, everything gets simpler. Okay, so what we want to do, we want to construct a homogeneous and isotropic description of the universe. What does it mean from, well, mathematical point of view? This means that we want to construct the metric which is homogeneous and isotropic. Okay? And here is this metric. Okay, so this metric is called Friedman, Lemaitre, Robinson, Volkel, Friedman. If you want to mention all the names there. So in different countries, different names go away. In the US, you will get Robertson-Volkel metric. In other places, you will get Friedman and then Lemaitre. Okay. So this metric, it has the following structure. So this is the interval. Okay, doesn't change if we change coordinate system. It's written in some coordinate system which makes its properties more or less obvious. Okay, so it's the t square. Then there is some factor which is called the scale factor of the universe. It doesn't depend on any place in the universe. It only depends on time. And then there is a piece which is the spatial part of FRW metric. Okay, and then this part is written here. So theta and phi are coordinates, spherical coordinates. Okay, so r is radius vector, and k here is the parameter which tells you whether the universe is spatially flat, open, or closed. Okay, so if you take, for instance, k equal to 0, then this part disappears, and what you see here is just the metric of Euclidean flat space-time, but written in spherical coordinates. Okay. If you take k equal to +1, okay, then you get the universe which is closed. How you can figure out that the universe is closed in this case, it's very easy. If k is positive, you see that this coordinate r, radial coordinate, can just run from 0 to 1, okay, telling that this space has a finite volume. Okay, and you can imagine that this is a three-dimensional sphere. And so if k is equal to -1, then the universe is open. It still has the constant curvature, but then now this curvature is negative. Okay, and this factor r, if it's taken to be constant, it would describe the universe which is static, not expanding, not collapsing, just static universe. And if we get the increasing r, that would correspond to expanding universe. Okay, so the distances between different points, physical distances, will increase. Okay, and it's difficult to make a three-dimensional picture, but if you think that the universe is just two-dimensional, then this is how we can visualize expansion of the universe. So imagine that you live on a two-dimensional sphere, and now the radius of this sphere is increasing. Okay, so this form of the metric allows you to establish theoretically the Hubble law. Okay, so what is the Hubble law? The Hubble law is a relationship between the velocity of the objects you find in the universe and the distance between them. So how you establish the Hubble law? Okay, you look here, and you find the physical distances between, say, two stars. Okay, and then these physical distances will be r times dl, where dl is this guy, and since you look in one particular direction, you can forget about the part which is associated with the angles. Okay, so you find the derivative of this distance. This part is just associated with coordinates, and coordinates are not changed. They're just attributed to different points in the universe. So this derivative is equal to r dot times dl. And so this means that the velocity, you divide this by that, you get r dot over r delta L, or you can write that velocity is equal to some constant. Okay, it's called Hubble constant. It's actually not constant. It depends on time, but it doesn't depend on space, times r, where r is the distance. Okay, so this is theoretical prediction. Okay. We can wonder how this theoretical prediction can be checked. And once you want to check some theoretical prediction, you have to formulate this prediction in terms of quantities which can be experimentally measured. Okay. The distance, as I already said, is not easy to measure. And also, how can we measure the velocity of the star which flies away from us? Okay, we are not there at this point. And so the idea here is to replace different quantities which appear in the Hubble equation by two other parameters, two other quantities, which can be measured directly in different observations. So one of them is the redshift. Okay, so what is the redshift? The redshift is the following. You take the wavelength of the light which is observed. You subtract from it the wavelength of the light which was emitted, and you divide everything by the wavelength of the light which was emitted. Okay, so how do you know these things? So that's what you measure, and the wavelength of the light which was emitted, you can see if there are different atomic transitions. Okay, so these atomic transitions, you can identify what kind of transition it was, and that gives you the definition of the frequency of the emitted light. Okay, so if you were in the flat space-time, that would be the quantity which is associated with the Doppler effect. Okay, so you know that when there is an emitter which displaces with a certain velocity, then the frequency of the light changes, and this frequency of the light, the change is proportional to velocity. Okay, so that was the idea of introducing the redshift in place of velocity in this formula. So yet another measurable quantity which we can use here is called luminosity distance. So the idea of luminosity distance is very simple. Imagine that, again, you are first in the flat space-time, the universe is not expanding, and imagine that you have at hand a standard candle. So what is standard candle? This is some object, luminosity of which you know because of some reasons, okay? Now, if the standard candle is at the distance, some distance from you, then you can find out this distance from the energy conservation, right? You basically say that all the energy which is emitted here is now distributed along the big sphere. Okay, and so that if you measure the flux of energy which passes through your telescope, and you know what the energy was emitted at the first place, you can simply find the distance from this formula. So this is the energy flux which you measure here. This is the energy flux which is emitted, and this is the area of this large sphere associated with our measurement with our telescope. Okay, so if you have that, you can determine this guy just by using blindly this formula, and then this is a measurable quantity which is called luminosity distance. Okay, so if you do so, and Hubble was the first or the second, people argue about that, whether Lemaitre was the first person who did this type of analysis. But anyway, this is the picture from a Hubble paper of 1929, in which he presented the Hubble law. So if you look at this picture from modern point of view, then it's somewhat confusing. Okay, so this axis here is the distance. So this axis here was supposed to be velocity, but velocity in his picture doesn't have correct units. And if you look at the scatter of points here, I would say that one has to be very brave to draw this straight line through these points. Okay. Well, also there are no error bars. The number which Hubble found himself in this picture was for the Hubble constant. Okay, so I remind you that the Hubble constant is this coefficient between the between the speed and, yeah, here. So you see that it has the dimensionality of 1 over yeah, I put wrong units myself here. Okay. There should be parsec here as well. Well, anyway, the number which he got is almost factor 10 from the current value. And if you look at the plots which are presented nowadays in different places, then you indeed find a straight line which goes through, and so confirming the Hubble law. Okay, so this simple dependence of velocity on r and the fact that r, that the Hubble constant which stands there is universal, is actually only relevant for sufficiently small distances between us and the place in the universe which we observe. So if we look at much larger distances, then the relationship between the redshift and luminosity distance becomes more complicated. We can understand why this happens. Okay, so suppose that, that this is the present time. We observe the star, and at some moment we received a light which is coming from this star. Okay, since light has a finite speed of propagation, then the light from the star was emitted in the past when the universe was much smaller. Okay, and therefore, in order to understand how we connect from this point to this point, it's clear that the evolution of the universe should intervene in between, so that the relationship between the redshift and Hubble distance should involve the way how the universe was evolved from this situation to that situation. Okay, and understanding of this fact happens to be very important because it allows us to pin down the content of the universe. It allows us to say how much matter there is in the universe, what is the cosmological constant of the universe, etc., etc. So what are the important steps to find these relationships? Okay, and I'm omitting here different details, important though. In order to find this relationship, we should be able to relate the redshift and the luminosity distance to the scale factor of the universe taken at different places. So for redshift, it's very easy to understand, and this relationship is here. The redshift is the ratio of radius factor here at present time divided by the scale factor of the universe at the time of emission -1. So this is almost an obvious relationship which you can derive in the following way. You take a wave, electromagnetic wave, and put it in, imagine that the universe is closed, okay? And then you put electromagnetic wave, which is kind of part of sine or cosine. And then you stretch the universe, okay? The number of wiggles remains exactly the same, meaning that the length wave behaves exactly as the scale factor of the universe. And it was the ratio of the wavelength of the electromagnetic waves which we fix our definition of the redshift. Okay, and so what you do, you replace lambda by r, and that's it. Okay, so this is the redshift. You can do the analysis of luminosity system, of the luminosity distance. So this analysis is somewhat more complicated because you have to take into account that there is the redshift, okay, so that the frequency of the wave changes when the universe expands. While the frequency changing, this means that the power going through your telescope is also changing. And so once you incorporate all these things together, you find that the university distance is the coordinate distance in FRW metric. And here there is some factor which accounts all these things. Okay, so you can check your intuition. You say, okay, let's say that T0 is T1. And then you find that the luminosity distance is given by that, and that's exactly what you would expect. Okay, so as I said, if you take sufficiently small luminosity distance, then the relationship is linear. The redshift is the Hubble constant times luminosity distance, and that was very high. For large d, this is not the case, and this relationship between z and d is more complicated and depends on the composition of the universe. It can be found, and it's written in some integral of some quantity which is well known. And this quantity takes into account the evolution of the universe between the time of emission of the light and type of absorption of the light. So how do we find this evolution? Okay, we have everything at hand. We have Einstein equations, which allow us to do so, which allow us to find this evolution. Okay, so we already said that the space is homogeneous and isotropic, and therefore we should also say, to be consistent with everything, self-consistent, that the distribution of matter is also homogeneous and isotropic. Okay, so we have to construct the stress energy tensor, which is homogeneous and isotropic, and a very good approximation is to say that the 0,0 component of stress energy tensor, just energy, okay, energy density, and whereas the Ij component of the stress energy tensor are associated with the pressure times Gij. Okay, so if you take this type of ansatz, you can show that the Einstein equation which you write are self-consistent. Okay, so left-hand side can be equal to the right-hand side, and the energy density and the pressure, they are function of time, but not the space. Okay, so once you do so, you insert the FRW metric to the left-hand side of Einstein equations, and you insert this stress energy tensor into right-hand side of this expression, and then you get Friedmann equations. Okay, so from Einstein you go to Friedmann in this way, and the Friedmann equations are written here. So this one, the first one is 0,0 component. So right-hand side is just associated with the energy density. Here we have derivatives of the scale factor. This factor kappa corresponds to the topology of the universe, open, closed, or flat. and these are ij components of the Einstein equation. Okay, so from 10 equations in total, remember that the metric is a symmetric quantity, you get just 2, and this is the consequence of the fact that the universe is homogeneous and isotropic. Okay, so now you look at this equation and say, we don't know what R is, we don't know what rho is, we don't know what P is, so there are 3 unknowns and 2 equations. So the system is not complete, and in order to solve it, we have to add something else, and this something else is called equation of state. And the equation of state is a relationship between the energy density and the pressure. Okay, and the relationship between energy density and pressure, it doesn't follow from this equation. It should be taken from somewhere else, and it's taken from somewhere else by specifying what kind of matter we have in the universe. So the simplest example here is non-relativistic matter. Okay, so you say that the universe is filled by, say, some particles, which, if they are moving non-relativistically, so that their speed, their velocities are much smaller than the speed of light. Okay, then in this approximation, we can say that pressure is equal to 0, okay? And if pressure is equal to 0, then that's it. The system gets complete, you can solve it, and the example of solution for 0 curvature of the universe, and that's exactly the solution which was found by Friedman first. You find that the scale factor grows as some power of time, t to the power 2/3, whereas the energy density has the structure 1 over time square. Another equation of state, which is important, and which we will be using, is that of relativistic matter. So in this case, you say that the universe is filled only by the particles which are going with the speed of light. Okay, in this case, pressure is equal to energy density over 3, and then you find the solution. Scale factor also increases with time as some power of time, and the energy density goes like 1 over time square. The third case, which is also very important, is that of the dominance of cosmological constant. So what you say is that in this equation, so this part is absent, this part is absent, so you solve them, and then you find that the universe, in this case, is expanding exponentially, and the rate of this exponential expansion is associated with the cosmological constant. Okay, cosmological constant must be positive in this expression, and I would ask you what would happen if cosmological constant is negative in this case. Okay, so these were 3 different behaviors which we discussed, and the more general case would be that in which there are all 3 components present. The components associated with matter, component associated with the radiation, and component associated with the cosmological constant. Okay, so in order to characterize the content of the universe, what is done traditionally is the following. The abundances of all these different components are introduced. How they are introduced. So the first thing is the introducing the critical density. So it's called density, but this is a geometric quantity. It is organized from the Hubble constant, which we measure today, and a Newtonian constant of gravity. Okay? So if you make this type of combination, you will find out that it has dimensions of the density, so that it's GeV to the 4th power. Okay? And then what we do, the abundance of matter is defined as the energy density in matter, and matter here is something which has equation of state pressure equal to 0, and you define that by the critical density. Okay, in this way you get a dimensionless quantity. Then this is abundance of radiation. Okay, and this is abundance of cosmological constant. So what you do here is that cosmological constant is here. Then you organize from cosmological constant some quantity which has dimensionality of energy density. And so you divide by 8 pi g, where g is Newtonian constant. So now this guy has a dimensionality of energy density, and then you divide it by the critical density. Okay, so in this way, you get these 3 abundances. And now you can do the following, okay? So in this relationship, which I didn't show to you, which contains some integral, etc., these quantities appear: omega matter, omega radiation, and omega lambda, okay? And the relationship between the redshift and, okay, here it's written magnitude. Magnitude is related to the luminosity distance, okay? In the case of the Hubble law at relatively small distances, you will get straight lines on these diagrams. And now if you include now large redshifts, then all these curves start to depend on omega matter and omega lambda, okay? And now by fitting these curves, you can extract the, you can do these measurements, and these measurements were done with type 1 supernova, so which you can see very far away at large redshifts. You can look at these measurements, and you can extract the values omega matter and omega lambda from these measurements. Just a small remark: there is a third quantity which appears here, which is abundance of radiation. You know what amount of radiation is around us. I will talk about that later. It's cosmic microwave background. So this number happens to be negligibly small and can be removed from the analysis. So what you are finding is actually omega matter and omega lambda. And this is what you get. So this was the first indication that well, not the first, I would say first very convincing indication that the cosmological constant in the present universe is not equal to 0. So what you see at this plot, here is omega matter, here is omega lambda. This is the omega matter and omega lambda, which were allowed by observations of supernova. Okay, so this is the ellipses of errors. The important point was that you see that this part is not touching 0, meaning that the cosmological constant is not equal to 0. there are other experimental measurements in this plot. So one of them is coming from observations of cosmic microwave background. I will be discussing somewhat later. Another line is coming from dynamics of clusters in the universe. You see that all these measurements, they have different type of degeneracies. So here it is, you cannot say where you are along this line. So here you cannot say where you are along this line, here like that, but they beautifully meet each other at one point, okay? If they were not meeting each other at one plane, that would be a disaster for this type of description. That would tell that we don't understand something very deep, or maybe Einstein theory is not true, but this didn't happen, and all this curve appear, intersect at one point. Okay. Perhaps I may comment about there are different lines on this figure. Okay. So there is this line along which the universe is flat. So that would correspond to omega lambda plus omega matter equal to 1. So if we were above here, the universe would be closed. If we were here, it would be open. If we are above this point, then the universe would expand forever. If we are below this line, then the universe would eventually recollapse. So meaning that it's now expands, but then it will reach some finite point and then start to contract. Okay, so this point corresponds to the universe which expands forever and is nearly flat. Okay, so the conclusions from that is perhaps one point here. So we are somewhere here, so you see that that corresponds to omega lambda about 0.7 and omega matter about 0.3, but I will give you better numbers at the next slide. So by this analysis, we see that the universe is accelerating with dominance of cosmological constant or dark energy, and it will expand forever. And the numbers of abundances are that we have about 70% of dark energy, about 30% of non-relativistic matter, from which 25% correspond to dark matter and 5% to correspond to baryon matter. Okay, and in fact, all these numbers, they represent the puzzle for the standard model of particle physics. Okay, so we will see somewhat later that if we believe in standard model as an ultimate theory, there should be 0. Okay. Dark matter, if we believe the standard model, should be 0 as well. Okay. Cosmological constant, it could be a part of standard model you just added. So this is the number which we cannot explain. So here there is not a big contradiction. Okay, so looking at that, we can ask many sorts of different questions. So what is the origin of this pattern? Why all these numbers are of the same order? Okay, we can ask all these questions, but we don't know yet the answers to all of them. Okay, so this is the end of first part I don't know if it's first, yeah, so let's say it's first part, which was dealing with general relativity and the structure of the universe. And now we are getting closer to particle physics. And so I'm going to start a new topic, which is Big Bang theory. There is no break, right? So I continue. And I have to stop at around.
Well, we start a little bit late. So we have 1.5 hours, so we stop at 10:40.
10:40. Okay, very good. Thank you. Okay, so we are coming. Yes.
Just a second.
Yeah. Please.
Just a second. Saying that the volume is very low. The volume is very low.
Yeah, please turn up the.
Okay, so we have to increase the volume of your mic. So
Yes, I don't think it's my.
he has a question.
I'm kind of struggling with the definition of pressure. What's pressure for you?
Sorry?
Pressure. What's pressure for you? Is kind of the statistical meaning of pressure? Or
Yes, so this is a normal statistical meaning of pressure. So it means that you put some wall, okay?
and surface and the energy transfer.
Yeah, you put some wall and then you consider the momentum transfer through this wall.
Okay,
so
great.
This is just normal, absolutely normal pressure.
Okay, so zero pressure, it's everybody in rest.
Yes, zero pressure is when nobody moves.
Okay, great.
Okay, so when I was talking about equation of state of non-relativistic matter, the pressure is still not zero, but it would be proportional to the velocity of particles inside. Okay, and the velocity of if the velocity of particles is much smaller than the speed of light, then the pressure is much smaller than the energy density, right? Because energy density is mass times c squared, mc squared, and the pressure is mass times velocity squared, okay? And so in this case, approximately, you can use p equal to.
Okay, great. Thank you very much.
More questions? It's a good time to ask questions because he's going to change
Yeah, because
topics.
I will start another topic. Yes.
What? Oh, there's a question. Can you read it?
So there's a question from Hani. He said, "Hi, I don't know if I understand it correctly or not, but you mentioned that by getting the variation of action of matter, we will get the right-hand side of Einstein equation. So my question is, if we have extension of standard model appear in action, will it encode in energy momentum tensor?"
The answer is yes. Yes, once you find the stress energy tensor, that all the stuff which appears in the matter Lagrangian will contribute to stress energy tensor, okay? But then, depending on the situation, the contribution coming from other sectors of the standard model, which we don't know, may be different. Okay, so for instance, coming back to the last slide, which I showed. So this puzzle can be formulated even here. This is not a part of the standard model, okay? So we do have now contribution to stress energy tensor coming from something beyond the standard model, which is actually even 5-6 times larger than the contribution which comes from the standard model Lagrangian, okay? And this is one of the puzzles. This is one of the indications that the standard model is not complete.
Okay, more questions? So I asked them to increase the volume, but do you hear the difference? If not, maybe Misha, can you speak a little bit up?
Yes, I will try.
Okay, just speak up.
Okay, I'll try to shout. Okay, so there will be a discussion session, okay, and they even said that we have to suggest exercises. So one of the exercises could be to derive all these lines which are on this picture from the Friedman equations. That's a very nice exercise, but I'm not sure you will have time to do it before discussion session. Okay, so now we are coming closer to particle physics. Okay, as I said at the very beginning, the relationship between particle physics and cosmology is due to expansion of the universe. Okay, and this relationship is done by Big Bang theory. So what I will do in this chapter, we will go very shortly through the summary of different behaviors which we can have in the early universe that you already seen, but here one important point will be underlined. Then we come to foundations on Big Bang theory, freeze in, freeze out, cosmic microwave background, photon decoupling, and neutrinos in the universe, where we will practice to use freeze in and freeze out conditions, which allow to understand really a lot of things in the universe without doing any complicated type of computations. Okay, so once more, if we have radiation-dominated universe with pressure equal to energy density over 3, then the density of photons or massless particles depend on R as this ratio to the 4th power. Okay? Why so? Again, very easy to understand. The universe is expanding. The number of photons there is conserved. Okay? Therefore, the number of photons scales like 1 over R cubed, but the energy of photons is redshifted, and redshift means that the frequency of photon goes like 1 over R. So these two factors together give you 1 over R to the 4th power. Okay? The Hubble constant is expressed through time as 1 over 2t, because R was scaling like time to the power of 1/2, and the energy density is 1 over t squared. If we have a matter-dominated universe, pressure is 0, rho scales like 1 over R cubed. Why so? Because these are massive particles which don't move. Their number density scales like 1 over R cubed, meaning that the energy density repeats this behavior. Okay, and this is the universe dominated by cosmological constant. Okay, so here it's non-trivial thing, which is counterintuitive, that the energy density associated with cosmological constant doesn't change. Okay, well, it doesn't change because this is just a constant which appears in Einstein equations. So if you look at the plot, which tells you how scale factor depends on time, then this picture is given here. So at the moment, the universe is accelerating. It expands exponentially. Okay, so it's this factor here. Then we go back in time. You see that when we go back in time, the energy density in the cosmological constant doesn't change, whereas energy densities in matter-dominated universe and in radiation-dominated universe are increasing. So at earlier time, different things dominate, And so what first dominates is matter, and here you have some period during which the universe expands as it had just matter, nothing else. And when you go back in time, then you find the moment where the universe is dominated by radiation. Okay, so again, why so? Because this behavior, fourth power, is more singular than the behavior in matter, which is just the third power. Okay, so if you look at the common feature of radiation and matter-dominated regimes, you find that there is mathematical singularity. So here you have 1 over time square, and in matter-dominated universe, in matter and radiation-dominated universe, you always have this 1 over time square singularity. Okay. So if we ask ourselves, okay, we found singularity, can we trust our formulas? The answer is no. The answer is no. Why so? Because everything what we were doing up to now was a classical physics. Okay, we never had h bar in our equations. And the whole physics is a quantum. There should be quantum corrections, and the most important corrections which show up when r goes to 0 is quantum corrections associated with gravity. Okay, and gravity becomes classical gravity becomes wrong when the densities of the system approach the Planck value. Okay? So Planck value is a combination of h bar, velocity of light, and the Planck constant, and this happens at the densities of the order of 10 to the 19 GeV. So all formulas gets wrong here. We don't know what is happening there. There are different hypotheses, different speculations at that point. We are not going that far. We're just going to stop at the time where we can still trust our classical formulas. Okay, and the main point here is that at the time when we can still trust our classical formulas, the densities of the universe are much, much larger than the densities we observe today. Okay, so the universe was much denser in the past. So for instance, if you take the average density today, which is about 10 to the minus 29 grams per cubic centimeter, roughly 1 proton per meter cube, that's the average density in the universe. If we take the age of the universe, about 1,000 seconds, we will find that the density is like water density. Okay, so saying that indeed these particles get close to each other. And just looking at that, we can reach a conclusion. And so Gamow reached this conclusion a long time ago, that the universe should be in thermal equilibrium at sufficiently early time. Okay? So what was the logic behind? The logic behind is that if you have interactions between particles, then you get a statistical system with very many particles around. And our everyday experience tells us that in this case, the system should move into the state with highest possible entropy. And the state with highest possible entropy is the state which corresponds to thermal equilibrium. There were predictions from this conjecture. The original paper of Gamow was about Big Bang nucleosynthesis, and we will go through this point somewhat later. It was written by Alpher, Beta, and Gamow. And somewhat later, using the same logic, the cosmic microwave background radiation was predicted. It's actually interesting from the point of view of history of physics, how this idea were developed. Okay, so roughly nobody believed on them. Okay, so for instance, a British astrophysicist Hall was saying that this Big Bang theory is actually Hall which pinned down the name for this theory, because he thought that Big Bang sounds very funny and it cannot be right. Okay, so he coined this as a Big Bang theory. Now we don't think that this is funny, but anyway, so he said that this is all complete garbage. It's also interesting that Zeldovich, whom I cited already, he was also completely against that. He thought that this is all complete nonsense. Okay, and so he wrote a review which appeared few months before discovery of cosmic microwave background, in which he said that this theory doesn't make any sense. Okay. And everything changed, or maybe 1 year, okay, everything changed back in '64 when Penzias and Wilson discovered cosmic microwave background. Okay. So this discovery also has an interesting history because it was discovered by chance, whereas other people, like Peebles, were trying to search for it, who believed in this prediction of cosmic microwave background, but they didn't make it. And other people, Penzias and Wilson, found it in '64. Okay, so what was found at that time and then confirmed later, that if you look in any direction in the universe, then you will find that there is a radiation which is called cosmic microwave background radiation, which has a exactly Planck spectrum. Okay, so arrow bar very, very small here, and these are the results of several experiments. Okay, and that's exactly what Big Bang theory would predict you, that the system was in thermal equilibrium at the beginning. This discovery, it put forward many, many important things. So for instance, it allowed us to determine the velocity at which the Earth moves through the rest frame of cosmic microwave background. Okay, so since universe is filled by matter, by radiation, there is a preferred system in which the cosmic microwave background is at rest. Okay, so we are moving through that with the speed of 370 kilometers. This is a dipole of cosmic microwave background. So this is the celestial sphere. In one direction, you see the photons which are coming to you with higher energy, meaning that the temperature in this direction is larger. Okay, in the opposite direction, the temperature is cooler, meaning that there is simply a Doppler effect, and you're moving through this radiation. Okay, so what will be important for us now is the following. So if you try to describe a statistical system which is not in thermal equilibrium, then this is a nightmare. Okay, this is very complicated because in order to completely describe the system, you have to give the velocities of all particles, etc., etc. And if you say that the system is in the state of thermal equilibrium, in a state with maximal entropy, this means that you can characterize the system by just giving a few parameters. Okay, and these parameters are temperature and chemical potentials. So in some sense, temperature is conjugated to energy, and this is associated with conservation of energy, and chemical potentials are the quantity which are conjugated to conserved quantities. Okay, and that, of course, gives us a simplification for describing the state of our system. Okay, so what kind of simplification it gives to us? So generically, we would give a distribution function. So distribution function tells you how many, the number of particles with a particular momentum. Okay, I will be discussing all the time the state of the universe, which is homogeneous, so no dependence on coordinates. And if the system is in thermal equilibrium, then you know what are these distribution functions. You have just to tell whether you have a boson or fermion. If it's a boson, you have Einstein-Bose distribution. If it's fermion, you have a Fermi-Dirac distribution. So here is plus for, oops. It's an opposite, I'm sorry. Yeah, so minus plus for fermions. And just using these formulas, you can find the quantities which are important for description of the universe. And remember, what was important for description of the universe, it was energy density and pressure. So if you take a relativistic limit, then you use, what is that? Yeah. If you take a relativistic limit, then you find the relationship between energy density and the temperature for Bose and Fermi case. You can find also the number density of particles for Fermi and Bose case. Okay, equation of state, here is pressure equal to rho over 3. You can consider also non-relativistic limit, and the formulas for non-relativistic limit are written here. This is the density of particles. If chemical potential would be very small, you find that if the temperature is much smaller than the mass of the particles, the number of these particles decrease exponentially, as you would expect. And again, so the energy density is just the mass of the particle times their concentration, and the pressure is much smaller than the energy density. I was talking about entropy. So the state of thermal equilibrium is the state of maximal entropy. The entropy, if you know the distribution function, is expressed through the distribution of particles with different signs corresponding to fermions and bosons. And again, entropy is simply temperature cube times some number which occurs when you compute all these sorts of integrals times some factor, 1 for Bose particles and 7/8 for Fermi particles. And this factor appears also in the definition of the energy density. Okay, so all formulas which I gave above, they were for one particle species. And now if you say that you have a plasma in which you have a certain number of bosonic degrees of freedom and fermionic degrees of freedom, then the energy density can be written as temperature to the 4th times some coefficient, where this coefficient is an important number which appears in many different treatments, which is a number of effectively massless degrees of freedom, which is sum over bosons plus 7/8 sum of fermionic degrees of freedom. Okay, so how do you count that? particle, scalar particle, it has spin 0, g is equal to 1. Massive fermion-like electron, g is equal to 2. Positron 2, vector particles such as W or Z, this is equal to 3. Massless particles like photon, G is equal to 2, because you have just 2 polarization. Say for massless graviton, it will be 2. If you have massless fermion, then it's 1, because you have just 1 polarization, left-handed or right-handed. Okay, and so this formula lead us to the main equation of Big Bang theory. So what is this main equation of Big Bang theory? From one hand side, if we take the universe, which is dominated by radiation, we know what is the energy density as a function of time. Okay, so this is the formula which we already seen. From another hand, thermodynamics tells us that the same energy density can be expressed through the temperature. Okay, so since this and this are the same thing, you can say that this guy is equal to this guy, and find from here a relationship between the Hubble constant and the temperature of the universe. Okay, and these formulas would be valid in radiation-dominated universe. And so here are the different numbers which appear here. So to remember, this is a nice formula to remember. If you express time in seconds and temperature in MeV, then roughly speaking, time in seconds is equal to 1 over temperature square in MeV. And that gives you the idea when the temperature of the universe was reaching this or that values. And here are examples of numbers. So if you take temperature of the order of 10 electron volt, 10 electron volt is an interesting number because 10 electron volt, roughly speaking, is a Rydberg energy, which corresponds to the energy of ionization of the hydrogen atom. Okay? And we will see that this number plays an important role in cosmic microwave background. Then temperature is of the order of this value when the universe is about 300 years old. Okay, water energy density maybe not that interesting. The temperature is of the order of 1 mega electron volt. This is an interesting number because it's a typical scale in nuclear physics. So few MeV corresponds to the binding energy between protons and neutrons inside nuclei. And this corresponds to the temperature of the other of nuclear synthesis. Okay, and presumably this is a good time to stop.
So questions? Yes, here and there.
In the beginning of your talk, you started saying that particle physics happens at one scale and cosmology happens at another very different scale. But because the universe expands, somehow, somewhere in the history, they were both on the same scale and then they were important. And then now in the final, we started talking about the Planck scale. And then, but Planck scale happened before the inflation. So my question is, would quantum gravity effects be relevant to explain the numbers of dark matter concentration, the baryon symmetry, or their effects would be diluted after inflation?
Okay. Short answer to this question is that we don't know. why we don't know? Okay, we say, okay, inflation. Very good. Inflation is a hypothesis which gained experimental support, but whether inflation happened or not in the past, strictly speaking, we don't know. Okay, it's very plausible that it happened. I would vote for that with my hands, but this is still a hypothesis. Okay. Now, if we accept this hypothesis that inflation happened, and if we again take most popular approaches to inflation, or even if you take experimental data associated with inflation, then this experimental data tells us that inflationary scale is much smaller than the Planck scale.
Smaller?
Yes. Yeah, I will talk about that at the last point, so that the energy density at inflation is much, much smaller than the Planck density. So in a sense, this is an experimental fact, because if that were not the case, then you would get a lot of gravitational waves coming from inflation. But these gravitational waves were not observed, and there is an upper limit on the contribution of inflation-generated gravitational waves, okay? And this upper limit tells us that inflationary scale is much smaller than the Planck scale. So if we take this stream of logic, then the answer to this question is no. No, there is no influence of quantum gravity on dark matter, assuming that dark matter was originated before that. But I would like to stress that we cannot give a clear-cut answer which is based on absolutely solid observations or absolutely solid theories.
Thank you.
Hello. When you were talking, when you introduced the fermionic and bosonic distributions, you analyzed both of them in the context of, in the limit of relativistic, in the relativistic limit and in the non-relativistic limit. And in both of them, you reached a equation of state. For example, in the relativistic limit, for both fermionic and bosonic distributions, you reached an equation of state, which was P equals rho over 3, which made me confused because if you have a fermionic distribution, you can have a matter-dominated universe, and it was previously established that the equation of state for that case, for the matter-dominated universe, would be P equals 0, which made me confused. Like, were you saying that if we introduce those distributions, we can have matter-dominated behavior even for bosons distributions?
Yeah, okay, so the answer, oops. Statement number 1, okay? Suppose that you have a relativistic system, even not in thermal equilibrium. It's just you have any type of system in which particles are moving with the speed of light. Then, in this case, pressure is equal to energy density over 3, independently on the nature of these particles. Okay?
Very curious. Thank you.
This is very easy to check. You take a wall, you take a particle which comes here, reflected, and you find that the only thing what matters there is the fact that the particles propagate with the speed of light. So this is a universal thing. And another universal thing is that if you now take now thermal system, system in thermal equilibrium, okay, and consider non-relativistic limit. Okay, then in non-relativistic limit, the distribution of bosons and fermions are the same. they don't feel this plus-minus Fermi-Bose effect.
Thank you.
Hello, it's working.
Hi.
I would like to know more about the Gamma hypothesis. I'm a bit puzzled because does it really hold in the primordial universe? Because if we consider the Boltzmann equation, don't we need a time-like Killing vector field to have equilibrium? So how do we reconcile the Gamma hypothesis
Okay,
with
this
that?
is the topic of the next lecture. actually.
Okay, so, okay, I'll leave to last.
Yeah,
lecture.
so the question was, okay, the universe is expanding, so there is direction of time, okay? So this is not a static situation, whereas thermal equilibrium is something which is static. So it looks like there is a contradiction between these two things. But I will discuss that next time.
Okay, thank you.
But in this case, we not consider the interaction between the different particles.
Yes.
This conjecture.
Yeah. So these formulas which were written here are for particles without interactions between them. Okay. So these formulas are for free bosons and free fermions.
Okay.
If the interactions are included, and as I will argue next lecture, these interactions are 100% important for the whole picture to be true, then these formulas are modified. Okay. So, moreover, even if you take a system in complete thermal equilibrium, let's forget about expansion. Let's just take hypothetical picture in which the system is static, there is some temperature, then all these formulas, they acquire radiative corrections. Okay.
Okay.
For instance, and there are periods in the universe in which this type of formulas happen to be completely wrong. So, for instance, you take strongly interacting particles, you take quantum chromodynamics. Okay? So this type of formulas would be approximately true if the temperature were much larger than lambda QCD, 300 MeV. Then there is asymptotic freedom, the interaction between particles are small, and the corrections to this type of formulas are of the order of strong coupling constant to some power, okay? Now, if you move to lower temperatures, this is all broken, or all formulas are wrong, and the computations has to be much more involved.
Okay, thanks.
I think maybe due to the time, we should move the rest of the question to the discussion.
The answers are short. So I think the answers are short. So one is if the 10 electron volt temperature is related to the 21 centimeter signal.
Yes and yeah. No.
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 The answer
no,
is no.
The answer is no.
The answer is no. The 21
No, this is Rydberg energy,
Yeah.
and 21 centimeter is the transition between two nearby levels.
It's much lower energies. And the other question is also by Juan Garnica, and he's wondering if you should take into account in the energy density of the universe gravitational waves.
Yes, you should take them into account, but they are negligibly small.
That's right.
So they can be neglected.
Yes. Okay, so let's thank Misha again for this talk. And yeah, I just want to remind you that this material is online, so you can have access, or something very close to this, right?
Close to this.
Yes, close to this is online. So please take a look. You can read everything there and come back with the discussion sessions. We're running a little bit late, so I suggest you start the lecture by Gustavo at 11:15. There's a coffee break outside.